Okay, good morning. Let's get started. Today we're going to talk more about nanoparticle synthesis and use this model system to build upon our picture of nucleation from last time and now talk about growth kinetics. In other words, once we form these nuclei of nanostructures, how does their size change with time and how does their size distribution evolve with time? The only announcements I have are the same as last time, the upcoming due dates, and also if there are any questions about the project proposal or the video assignment, please go ahead. Okay. So last time I presented an overview of different methods for synthesizing nanostructures, and I wanted to illustrate by a bunch of examples of different systems and different types of structures that there are a lot of different ways you can end up with the building blocks that we're considering in this course: nanoclusters, nanoparticles, nanotubes, nanowires. But I think there is one common theme in that I'd like to view them all as nucleation and growth processes. But in the examples that we overviewed, we saw that you can have processes that happen in a bulk. For example, in a liquid solution where we are controlling the conditions to cause nucleation of clusters by supersaturation, by raising the temperature, or for example, by raising the concentration of precursor. A similar thing could happen in the gas phase by evaporating a precursor from a crucible, for example, hitting a solid with an electron beam or thermally heating that solid to create a vapor and supersaturate the vapor atmosphere. And we can form these structures in the bulk, or we can form them on surfaces, or you can do intermediate things where you form some kind of smaller clusters in the bulk or in the gas phase, and then they stick on the surface, and then they move around on the surface and form larger structures. And this is really a broad universe of processes, and we haven't really started to talk about and won't talk about a lot of cases of what the atomic mechanisms are, what the specific chemical steps are. But I think that grasping qualitatively the principles of nucleation and growth, separating those events, and understanding the limiting aspects of a few model systems can give us a general understanding of how you approach the process of synthesizing a bunch of different types of structures. And certainly we also saw that what I'm calling in the second bullet here a single-step process or a multi-step process means, for example, that in some cases we would make just nanoparticles in solution and then be done with it. In another case, we may make particles in solution and, say, deposit them on a substrate and use them as catalysts for growth of nanotubes or nanowires. Or, for example, we could deposit nanoparticles by, say, a gas phase method and then change the atmosphere to then grow carbon nanotubes from that arrangement of nanoparticles. And there are also cases that were somewhat analogous to deposition and growth of thin films, where the characteristics of the substrate and or the crystal structure nature of the material we're depositing can, under certain conditions, cause evolution of nanowires without any specific growth sites or any specific catalysts. And the example that we discussed briefly was growth of zinc oxide nanowires, where on a surface with some roughness, you get heterogeneous nucleation from the gas phase, i.e. formation of clusters of a critical size, just kind of like we're thinking about in the elementary model of solution growth. And then after that, because of the anisotropy of the zinc oxide structure, it's favorable for wires to grow along a particular axis. And we'll build more upon this model on Monday when we talk about the specific examples of nanotube and nanowire growth, how the size distributions of these longer structures evolve with time. And I'd like to say there are a lot of analogies and similarities to processes that have been studied for a longer time, deposition and growth of thin films, but here we're trying to think about what happens really in the very early stages. So our main picture is that we start our process, we nucleate these small clusters, and then we enter another stage where we go from nucleation to growth. And our goal, and the goal that's said over and over in all the papers that we're reading, and the driving principle of this process is to separate these two events. If the goal is to have a monodispersed size distribution in the end, you want to form these starting structures suddenly and uniformly, and then you want to transition to a state where you are increasing the size of all those starting nuclei in a uniform fashion. And today we'll see, after we have created those nuclei, the ways in this simple model that one can control the size distribution of the particles. And it actually agrees very beautifully with the observation we saw about how, for example, injecting more precursor into the solution to increase the supersaturation can change the growth dynamics. And what's happening is you are affecting how much source that each particle sees, and that affects the relative consumption of source by particles of different sizes, and therefore puts the population in a regime where the growth rate depends on the size of the particle or does not depend on the size of the particle. And for example, if you have, in all cases, you're going to have a size distribution. You're never going to have everything exactly the same. But if, for example, larger particles grow at a slower rate, then that means that as time proceeds, the small ones will catch up to the big ones and your size distribution will focus. And that's exactly what is seen and confirmed theoretically and experimentally in the example that we are addressing. So, we can consider all the formation of all of these structures as starting from, one atom or a small number of atoms. And, like I said before, we really aren't thinking exactly about how the atoms are coming in, but there is just some source material and it's decomposing at a surface or in a bulk and aggregating together, and the primary steps of accumulation are leading to evolution in the size of the structure. And this can be, a spherical cluster like so. It can be an elongated structure where the crystal organization of it or the presence of a catalyst particle, as we'll see next time, has a role of precipitating out a linear form when this structure itself is supersaturated. For example, a gold droplet is supersaturated with silicon by forming a eutectic. Or, in fact, in the growth of sheet-like materials such as graphene, you have a planar heterogeneous nucleation and growth on a surface. You form a small island, and then that island grows out in a planar fashion, and you end up covering the substrate with layers, and perhaps additional layers are created by nucleating and growing more layers on the surface. So it is like a very controlled monolayer crystal growth in one example of how these two-dimensional sheets are made. So then today we're going to transition from nucleation to growth, and we'll address what's called diffusion-limited growth and reaction-limited growth. And then we'll use these basic ideas and definitions to build a model of the evolution of the size of nanoparticles in solution. What governs whether the size distribution broadens or focuses, whether the standard deviation increases or decreases. And then we'll close with some examples of a couple other methods, chemical methods of nanoparticle synthesis, that embody the same principles but give specific examples of how the chemistry and temperature and concentration are controlled to make different materials and also different shapes. And then on Monday, we'll conclude this discussion of synthesis by relating to nanotubes and nanowires and talking about means of integration with top-down methods of lithographic fabrication. And the readings are the same list as I presented last time, and just to give us a reference, we're focusing primarily on the green papers at the top, and you'll see that my written notes are now posted on CTools, and the second section that we're addressing today comes largely from the Sugimoto paper, indeed only the early stages of the paper through page 73. You don't need to look at the rest of it. Okay, so last time our discussion of the thermodynamics of nucleation came down to this idea of a critical size, that when you have an environment such as this room and increase the concentration of precursor, you create a supersaturated situation. And at a particular supersaturation, there is a size of cluster that will grow, and there is a size of cluster that will shrink. And this size is called the critical size. And if you look at the free energy change that is associated with forming a cluster of a certain size, and you see the size at which the free energy change with size is a first derivative of 0 here, that tells you that clusters beneath that size will shrink and clusters above that size are going to grow. And this is a computation following the theory for different metal crystals at certain conditions. And our final answer was that the critical radius was related to the surface energy of the material and its atomic volume divided by the thermal energy times the natural log of S, which was our supersaturation. Which, for example, can be in terms of a pressure, such as a vapor pressure of a precursor that's condensing into liquid droplets, or today we'll kind of talk more about solutions, and so this could also be C, a concentration. And we saw at the end this experimental result of how by adding extra precursor to a solution, without thinking about the exact chemicals that are in the solution, we're able to observe, and remember these measurements were made in situ by looking at the optical properties of the nanoparticles that we know depend on their size, that the size distribution changes with time. So for example, when nucleation is induced by having a hot solution of the solvent and injecting a desired amount of precursor with the syringe, then we start to see formation very rapidly of particles of a particular size. And then as that process proceeds, the growth regime begins and the size increases gradually. And so you have a nucleation event occurred by injecting the precursor, and then a growth event that goes on like so. And it so happens that in this process, in the initial stages, we see that the standard deviation decreases. We don't pay attention to this point because it's kind of off the charts because the particles aren't formed yet. And then as the amount of precursor is depleted, the standard deviation starts increasing. And in this case, the size distribution is focusing, it's narrowing, and in this case, the size distribution is broadening. The standard deviation is increasing. And then what happens is when another amount of precursor is injected, then the dynamics reverse. The standard deviation starts focusing. And what's happening here is by increasing the relative supersaturation, we're going into a regime, and we'll see the bounds for this regime quantitatively in a little while, where the size distribution now starts to narrow. In other words, the dynamics of growth of particles, each one has its own size and growth rate, are changing such that the small ones are catching up to the big ones. But overall, they are all still growing. The average size is increasing. But this is the classical technique of managing the dynamics of growth after the dynamics of nucleation happen. And another thing that's mentioned in this paper is that during the focusing process, the number of particles in solution is constant. So by injecting this extra precursor, they're not in a situation where additional nucleation is happening. That would be bad. But we're in a situation where the solution is still supersaturated, but the critical size is lower than the average size in solution. So all the particles are growing, but there are no new particles being created. And then in the case of defocusing, when the size distribution is broadening, it's actually the case where smaller particles are disappearing. So it means that the critical size relative to the mean size is in a case where there are a significant number of particles that are shrinking, and that's causing the size distribution to broaden out. And we'll come back to this at the end when we understand the quantitative bounds for these cases. So over 50 years ago, the first paper that talked about this process of nucleation and growth of colloidal, colloids in solution or small crystals, just kind of very elegantly plotted out the idea that we're trying to describe by decoupling the nucleation and growth processes. So the schematic here has concentration of the precursor on the y-axis and has time on the x-axis. And there are three concentration values on the y-axis. There's the solubility of the eventual size of clusters in solution, and there's the minimum concentration for nucleation, and then there's a maximum supersaturation at which you just get precipitation of a lot of the material. And what it's showing here is that if you, say, increase the concentration suddenly, then nucleation will happen, and because nucleation happens, the nuclei consume precursor, then the concentration drops down beneath this threshold, and growth by diffusion, and we'll learn about diffusion now, happens as precursor goes to the particles, and the particles increase in size and end up at a size where they are in equilibrium with the surroundings. So if we, for this one point, hold the idea that all the particles are the same size, then you're going to end up with particles that are exactly equal to the critical size, that won't grow or shrink in the solution because their size is in equilibrium with the surrounding concentration of the monomer. Clearly, you're not going to consume all the monomer or all the precursor, because then that would mean the particles would dissolve. So in the end case, you have some precursor left over, and you have some particles, and the particles are in equilibrium with their surroundings. Now, when you have a size distribution, it's a more complex case, because some particles are bigger than others, and you have ripening happening. But in the basic case of, example, imagine one particle in a solution, then you have, in the end, a case of equilibrium where its size is equal to that governed by its solubility. So I want to introduce two basic sort of modes of growth or modes of reaction, and I'm sure many of you have heard of these in contexts of chemistry and kinetics, but to state them to start for us, we're going to consider the case of a diffusion-limited growth or diffusion-limited kinetics. And what this means is that the rate of a reaction, or in our case, the rate of growth of the particle in solution after the nucleus forms, is controlled by the rate of transport of the reactants or the monomers, whatever is adding itself to the particle, through the medium. For example, it's like the transport of the monomer through the solution to the surface of the particle. Or it could be, if the case of nanotube growth, it could be the rate of transport of carbon through the particle surface, over the particle surface or through the particle to the nanotube. But for example, if you have a solution and you stir it so you're able to more rapidly provide precursor, sort of refresh the zone of precursor around each particle, and the growth rate increases, then that would tell you that the process is probably diffusion limited. And in the opposite case, a reaction-limited case is exactly what that would sound. And in that case, you have enough precursor feeding to the surface, but the rate of growth is limited by the rate of the surface reaction, because you not only have the transport of the reactants or the transport of the precursors through the solution to the surface, but once they're right next to there, then there is some step that needs to happen for the precursor to hook on. And in you could say that the simplest case, the one we're going to consider today, is just having a solution with a particle in it and having this imaginary precursor come diffuse through the surface, diffuse close to the surface, and then that's one step, and then the second step is when the precursor sort of hooks onto the particle and becomes part of the particle. But in other cases, we could consider that there may be many more steps. For example, if you have a gas phase process or a liquid phase process that involves, say, first a dissociation of a molecule, and then a transport of a molecule, and then some addition to the surface, and maybe once it adds to the surface it diffuses, and it might react with something else and desorb and so on. There are a lot of cases where the processes are much more complex. And things like the diagram I showed briefly last time, where you might have multiple limiting steps, and you may have to analyze the process to understand what step is actually limiting. But if we consider these two basic cases, we can, for example, consider how these regimes may be at play or not be at play if we had, for example, a different amount of precursor in the solution. Because if the reaction rate is a certain rate and we have a very high supersaturation, then you can imagine that we're more likely to be in this reaction-limited regime. We're supplying enough precursor no matter what rate the particle wants to grow at. But if we have a low concentration of precursor relatively, then it could be that we're going to be limited by diffusion. We're not providing enough concentration gradient between the surroundings and the particle to grow the particle at the rate that it wants to grow by the basic reaction. So we're going to start building upon our model of nucleation by now imagining that we have a particle, a nucleus of radius r, and it's surrounded by a solution. And we're going to model, without considering the real details of the reaction, what the chemistry is and how the monomers absorb and react on the surface, this process of
a monomer coming from the bulk solution and diffusing across this layer, which we'll say has a thickness delta governed by the distance from the center of the particle, which here is shown x, and we will call it r. And it diffuses across this distance, and then it eventually adsorbs on the surface of the particle and adds 1 unit to the particle's volume. And going with the terms that are defined in the reading, we're going to call C sub B the bulk concentration of the precursor in the solution, and we're going to call C sub I the concentration at the interface, and then we're going to call C sub E the solubility of the particle, or it's the kind of the concentration of monomer in the solution at which the particle would be in equilibrium. It would not be growing or shrinking. So that's essentially the concentration dictated by the critical size of the particle itself. And we'll see under different regimes like what the relative values of these concentrations are. And we're going to start from the first principle of diffusion and develop this growth model. So to do this, we're going to start by stating the first law of diffusion. By modeling the diffusion across this layer of thickness delta. So as you can see here, we have a concentration gradient, or a difference in concentration from the bulk to the interface. And we're going to assume that this is a first order reaction, so that this gradient in concentration is linear. We're also assuming, as you can assume from here, that the layer is flat, so the curvature of the particle is large compared to the thickness of the layer. And from this, we can state that the flux of monomer J to the surface of the particle is equal to minus 4 pi times the particle radius squared, so the surface area of the particle, multiplied by the diffusion constant, or the diffusion coefficient, multiplied by the concentration gradient. And we'll call this dc dx, or kind of equivalently, we could call it dc by dr if we say that our coordinate from the center is x or is r. And this would be, in context of diffusion, what's called Fick's first law. So if we want to basically quantify how much monomer is crossing this layer, when we have a certain concentration gradient across it, we can integrate from the position r to the position r plus delta. So if we reorganize this equation, so we have j over 4 pi d on the left side, and have our, the r by r squared on the left. Then on the other side, just have dc, and we integrate from r plus delta to r, and from at r plus delta, our concentration is the bulk concentration, and at r, our concentration is the interface concentration. We get the result that we have j over 4 pi d times 1 over r from r to r plus delta being equal to just the difference in concentration from the interface to the bulk. So now if we evaluate this integral at r and r plus delta,
we'd get that we have J over 4 pi d multiplied by 1 over R minus 1 over R plus delta equal to Ci minus Cb. And then we can just rearrange, collect the terms here in this expression. So we would multiply this equation by this term by R plus delta and this term by R, and we would get delta over R times R plus delta being equal to Cb minus Ci. Just R plus delta in the numerator here, minus R divided by the product of the denominators. Yes? I don't know why I switched that. Thanks. And it makes sense here that if Ci is less than Cb, this term is negative, and so in our coordinate system, the flux is negative, or the flux is toward the surface of the particle. So now if we just rearrange the previous equation, so J is isolated on the left-hand side, we would get that J is equal to 4 pi d times R plus delta divided by delta multiplied by sorry, once again, I switched it. So this is an expression that governs the diffusion of the monomers to the surface. And now if we look at the reaction at the surface, because all the monomers that diffuse at the surface need to react at the surface, we can write another equation that accounts for the reaction constant, or the reaction rate at the surface. Because, you know, over the reaction we're assuming is in steady state, all the monomers that go to the surface react. It's not like they go at a faster rate than react, and you build up, you know, a layer of monomers ready to react at the interface. So now if we look at the surface reaction itself, we can write the same J, because we know that J due to diffusion is going to be equal to the J due to reaction, that the J due to reaction is just the surface area again, multiplied by a K, which is the rate constant of the surface reaction, multiplied by the difference Ce minus Ci. So now I'll say this is orange, this is J for the surface, and this is J for diffusion. And so if we set these two as equivalent, Js equals J sub d, and we then take a ratio of the concentration differences, we would end up with the result that Ci minus Ce divided by Cb minus Ci equals the diffusion coefficient divided by the reaction constant times R times the quantity 1 plus R
divided by delta, which just comes from dividing this expression here by r squared. You have an r squared term here and an r delta term here, and divide those by r squared, and you end up with this term here. So I'm switching both the signs of both here. Ci minus Ce and Cb minus Ci. So now we have a general expression that equates the transport to the surface with the reaction at the surface. So now if we look at the first case where we have diffusion limited growth. We can make the following assumptions. We can say that the concentration at the interface is equal to the equilibrium solubility of the particle because we're limited by the rate of supply at the surface, so there's no concentration gradient at the surface that is accounting for a slower reaction rate. In other words, the reaction rate at the surface is consuming the monomer as quickly as it comes in. So this just means that, in concert with the previous diagram, in the previous diagram we had this case, that was Cb, that's Ci, and we had a Ce down here. It means that we're going right down to this level, and the interface concentration is equal to the equilibrium concentration. And therefore, from the previous relation we had, the definition we had for the flux due to diffusion, we can say that J due to diffusion is equal to 4 pi dr times r plus delta divided by r. I'm just copying down the equation from above, multiplied by Cb minus Ce. There should be a minus sign there. And because there's no concentration difference here, nothing we have to account for specifically for the reaction rate slowing us down, we can now directly relate this flux to the rate at which the particle increases in size. So now let's just think of how much the volume of the particle will increase if it is supplied with this flux of the precursor. So we can set this diffusion flux equal to the equivalent flux required to increase the particle, and we can state this as being equal to the surface area of the particle divided by the molar volume multiplied by the rate of change in its size. So here we have an area, here we have a length per time, and here we have a volume. So we end up with the units of flux, which are just 1 over time.
or the number of atoms that arrive at the surface per second. So now all we have to do is rearrange this equation, these two sides of the equation, the right side and the left side, so we isolate the term for the change in radius, and then we're going to see what it depends on. So if we collect terms from both sides of the equation, we would get that dr by dt is equal to the diffusion coefficient times the molar volume divided by the radius times r plus delta divided by r multiplied by our concentration difference. And we can just divide this by r and bring in the r from the outside and get that this is equal to 1 over r plus 1 over delta multiplied by CB minus CE. So this tells us simply that if CB is greater than CE, or the bulk concentration is greater than the equilibrium concentration, then dr by dt is greater than 0, or the particle grows. And if the opposite is true, dr by t is less than 0, and the particle shrinks. And it also says that if we assume that our diffusion layer delta is constant and that our difference CB minus CE does not depend on R, then as R increases, dr by dt decreases. In other words, if this term is changing and the other terms are constant, as 1 over r, as r gets bigger, dr by dt gets smaller. So that means that larger particles in this diffusion limited regime, making the assumptions I just stated, and we'll see a limitation to this assumption in a little while, the bigger particles grow at a slower rate, which means that if you have a distribution of particles, the smaller ones can, at some rate, catch up to the bigger ones. And if you think that now in the context of the dispersity of the distribution, the standard deviation of the size, the particles are getting closer in size, closer in average size with time. Of course, all the particles are growing, but the small ones are catching up in size to the big ones. And in other words, this tells us, this is T, that the size distribution is focusing. So the standard deviation is going down. Yes? Mm-hmm. should be divided by R. Are you pulling it from a different equation or just?
No, I mean, from the first one to the second one,
Mm-hmm.
you get the
Yeah.
1 over R plus 1 over delta, then the first line can only be B times B and divided by delta
Okay.
times R plus delta divided by R. Otherwise,
Yeah. Yeah, you're right. I think. The mistake is this. There should be a delta on the bottom here. I wrote that wrong. Sorry. So now R over delta divided by R is 1 over delta, and delta over delta divided by R is 1 over R. Sorry about that. I knew there was an R on the outside. Okay. So now let's consider the other case where we have reaction limited growth. And if we go back to our picture of the concentrations, where we had CI, CE, and CB, and we had this gradient, if we assume the limiting case where now we're getting as much monomer to the interface as we need, then this difference is going to exist because there's going to be a concentration gradient very close to the particle surface, limited by the reaction rate, not by diffusion, but the relative magnitude of that is going to be very big compared to the magnitude of this difference. So therefore, we can now say not that CI is equal to CE, but that CB is equal to CI. So you really have a gradient driven by the reaction at the surface, and and no gradient going away from the particle as a limiting approximation. So now we can write that the rate of change in the particle size is equal to the reaction constant times the molar volume times the value CI minus CE, or the same thing, given our assumption, would be saying that this is equal to CB minus CE, because CI and CB are equal. So now if we assume, again, that the concentration difference at the interface, the important concentration difference, is independent of the particle size, now it's saying that the rate of change in the radius is the same for all particles, which would mean that a 5 nanometer particle, say in 1 minute, becomes 6 nanometers, and a 10 nanometer particle at 1 minute becomes 11 nanometers. So we're certainly not focusing the distribution. And if we kind of relax these assumptions, it would tell us that the case is worse, and in fact the distribution is broadening, because it would relate to considering further details of the kinetic steps at which the monomer actually adsorbs on the surface and then kind of creates another layer. And this is mentioned in a bit more detail in the reading, but it's really not important for what I want us to consider. I just want to think about how in these different regimes, the relative rates of size increases for different sizes might be different. So now there's one more thing that we can do, and it gets us through a bunch of steps to a final answer that lets us more precisely relate the change in size of the particles to the change in size to their size relative to the critical size existing in solution. Because we could think of like changing the concentration so we are at a certain position
between the equilibrium concentration and the critical concentration for nucleation of clusters of a certain size. And the considerations for this get mathematically a bit more involved, so I'm not going to go through it, but I just want to jump to the final answer that's in Tsujimoto, and we're going to look at the end answer and we're going to think about what it's telling us about how the size distributions evolve. But we're not responsible for being able to drive between here and there. So what comes out finally by now relaxing the assumption that the difference in concentration is independent of R. So now we say it's dependent on R, and that we are in the diffusion limited regime. Then it's shown quite rigorously if we define that R bar is the mean or average radius, or particle size in solution, and that delta R is the standard deviation in radius. So these are just the symbols that are used. It could be R bar and sigma. Then what's shown is that the rate of change in delta R, the standard deviation, is equal to a constant, which I'll fill out in a second, k sub d, multiplied by the standard deviation, divided by the mean squared, multiplied by the quantity equal to 2, divided by the mean radius minus 1 over the critical radius, R star. And, let's think, sorry. I didn't mean to cross that out, I just meant to circle it. There we go. And R star is the size that would be in equilibrium at the concentration C sub E. So this says that at a particular point in time, so at a particular point in time you have a certain average size and you have a certain standard deviation in size. So R bar is what it is and delta R is what it is. If we sit at that point and we think, well, what's the derivative here? Is delta R increasing or decreasing? Is the size distribution broadening or focusing? That the sign of this term will change based on whether this quantity is positive or negative. So I just want to write this better as a 2. So it says that d delta R by dt is greater than 0 if R bar divided by R star is less than 2, and d delta R by dt is less than 0 if R bar divided by R star is greater than 2. So the rate of change in the standard deviation, the breadth of the distribution, whether the distribution is getting fatter or getting narrower, depends on the ratio between the mean size and the critical size at the particular conditions we're operating at. So, concentrations aren't in this equation, but there's a concentration associated with all this based on the conditions of the situation. And that's kind of telling us why changing the concentration in that experiment let us go from the regime of broadening of the distribution to focusing of the distribution. Because if at a certain point in time we have a particular mean size, R bar, if we increase the concentration, what happens to the critical size? It goes down, because higher concentration, higher supersaturation means smaller critical size, means smaller nuclei are more stable because you're more ready to form them. So if we increase the concentration, so we cross the boundary between, the ratio of the mean size to the critical size being equal to 2, then we go from a regime of broadening to focusing. And, the real situation's a bit more complex because of, the nature of the distribution and multiple steps of reactions and so on, but this agrees pretty well with the observation made in the experiment that the distributions broaden and focus by changing the concentration. So this is just a plot from the Sugimoto paper that is just showing the result of this expression. And here we're looking at the rate of change in the average radius, and here we're looking at the rate of change in the standard deviation of the radius, or the breadth of the distribution. And you can see here that as a function of the value of the critical concentration, if the average radius is equal to the critical concentration, then the particles are neither growing nor shrinking. And as the value of the average radius relative to the critical concentration increases, then the growth rate of the particles actually reaches a maximum and then goes down. However, the rate of change of increase in the standard deviation goes from being negative to being positive as you go, or from positive to negative as you cross this boundary of twice the value of R star. And I don't want to think more about whether this boundary is actually smaller or larger, but let's just remember that there is a critical difference in regimes between the case of broadening the distribution and focusing the distribution. And it relates to the way that monomer is supplied to the particles and how the growth kinetics of individual particles depend on their size. So to kind of just complete the picture, we can go back to the plot we had from the Peng paper and just now think about when they're injecting more precursor later on, they're creating a situation where the value of the critical radius under these particular conditions is sufficiently smaller than the average radius such that you go from a regime of broadening the size distribution to focusing the size distribution. And just as the plot on the previous slide would tell us, if you go closer, if you cross into this regime, then you increase the growth. You also make the growth rate of the particles greater, but that comes with supplying more monomer, but you're not necessarily making the distribution broader. Okay, so that's the end of that example. Are there any questions about what we came up with? So keeping on this principle of separating nucleation and growth, and also thinking about some other things that we haven't talked to, like particles of different shapes and ways that you might stabilize particles, like maybe we can control this process very well, but say we want to stop it at a particular size. How would we do that? Or how do we end the process? Cool it down or maybe add something else? Depends what you want to do. We're going to start to see answers to a couple of those questions just by way of a couple of examples. And these examples do somewhat different things, but keep with the same idea of separating the events of nucleation and growth, which is absolutely necessary to create structures that are monodisperse. So we'll spend the next few minutes talking about this paper from 2004 that presents a chemical process for creating very highly monodisperse nanoparticles of iron and other metals and metal alloys by kind of a different route than was in the Peng paper. And this is not in your list of readings. You don't need to look it up. I just want to give this example of how their process works. And so what they do is they start out with a metal salt here, and this is a general diagram for a bunch of specific processes they do. So for example, a metal chloride like iron chloride, FeCl3, this is a fairly low-cost salt, and then a compound of, say, sodium and oleate, which is like the derivative from oleic acid, which is a fatty acid that's found in a lot of fats and vegetables and animals and so on. For example, there's a lot of oleic acid in olive oil. And what happens is they're able to heat up this mixture of this metal salt and this sodium oleate compound such that you form a complex between the metal atoms and the oleate. For example, in the case of iron, it's iron with 3 oleates around it for each iron, and the salt, which is the other things that you aren't going to use, sodium chloride. And this happens at a relatively low temperature at about 70 C. And then they're able to take this metal oleate complex, the salt precipitates so they can separate out the salt, and they can heat it up in a controlled fashion. So they observe a nucleation event happening in the case of the chemicals they're using at about 240 C, and a growth event happening at about 320 C, and wow, in the end they get very highly monodisperse nanoparticles. And it's the ability to separate these two events that makes the process give a very highly monodisperse result. And what's really interesting is how they understand how and why this happens. So what they found, and what's shown in the supporting information to their paper, is that in the first step, the step that happens at 70 C, you form these iron oleate complexes that have 1 iron and 3 of these long tails. And they're able to show that at about 240 C, what happens is this iron oleate loses one of its oleates, and then that one goes away, and you can form nuclei that are essentially 2 irons and 4 of the oleates. So you're able to create highly monodisperse nuclei in one step. And that is separated by a big distance from, question?
It's iron oxide or
iron? So I think they end up making iron oxide particles in the end. And they can make a whole bunch of other things. And then at 320 C, they suggest that the other ligands come off and they can enter a growth regime where you have primarily irons and eventually iron oxide because of the conditions of the process forming in a relatively uniform fashion. And there still is a size distribution happening, but because you can start from these highly monodispersed nuclei and go from a distinct nucleation regime to a distinct growth regime, you end up with relatively monodispersed particles. And the plot that we've been looking at for a while here is a measure of the weight loss as a function of temperature of the solution and a measure of the heat flow that occurs into the solution. So in this case, it's a fairly endothermic process when the solvent decomposes and boils away at about 320 C. And they're able to show that in their nucleation process, they lose just under 1/3 of the weight because they're decomposing that first molecule, and then when they boil the rest of it away and they grow, they end up with only the nanoparticles remaining. And when they do the process and, for example, show the product when they've done the nucleation step and then done a growth step at 310C before the boiling point of the solvent when they decompose and grow it, they have basically nothing there, or no well-defined crystals, maybe a few large clusters and complexes here and there. But if they process it at 320C for a very short time, basically they're just heating it up to 320C and then cooling it down, so they call that 0, or 10 minutes, or 20 minutes, or 30 minutes. Now these are done ex situ by doing the process and then looking at the particles in the TEM. They see that they get a fairly consistent increase in the size of the particles. And it's not that the nucleation and growth events are totally separated, that no growth happens in the nucleation regime, but for example, they can study what happens if they repeat their process, but they use very, very long nucleation times. So they hold, for example, the material at 260C for a day, or 3 days, or 240C for 3 days, or a lower temperature 200C for 3 days. And you can see that the size distribution of the particles in these cases, when they have a longer duration at the nucleation temperature, is broader, because you're taking some nuclei and they're forming into larger particles, while you aren't taking a short nucleation event, just forming the single nuclei, and then going to a higher temperature where growth is much more instant and much more rapid. So in this case, it's kind of another way, based on the particular chemistry, to produce monodispersed clusters by separating these nucleation and growth events, but you end up with the same principles at work. And they also, if you were to look into the paper, you would see that they can, by controlling the solvent and changing the boiling point and changing the concentrations of the particular components in solution, these are just other knobs that can be turned to control the sizes of these particles. So the details and the reasons why aren't important, but this is a compelling picture from this paper that shows that because this can happen in solution over relatively large volumes, it's a very good way to make large quantities of these powders, which end up being made from fairly monodispersed crystals. And as you can imagine, in terms of magnetic properties, iron oxide has interesting magnetic properties for data storage, as well as if these were semiconductor particles, having a high monodispersity in the size distribution is very important for the properties. Another thing that we'll talk about in a couple weeks is the way that particles pack by self-assembly, and you can see that this is a picture of, for example, a droplet of this particle solution that was dried on a TEM grid, and you can see that you have some locally hexagonal packing. And it turns out that the process of packing, kind of like we saw for nanosphere lithography that we introduced before, is highly dependent on the standard deviation or the monodispersity of the particles. You get a lot better packing if the particles are more monodispersed. And so processes like these that make highly monodispersed particles are necessary for getting them to self-assemble and pack with high order over large areas. And that idea of packing is kind of why you see that some of their TEM grid images not only look very uniform in size, but also have the particles nicely packed together. So that's a kind of practical ramification of the ability to make these particles with pretty uniform size distributions. And the paper goes on to talk about how by changing the materials involved, they can make different particles. They can, for example, make iron cubes or cobalt oxide structures or manganese oxide structures by changing the characteristics of the precursor. But this idea of thermally decomposing a solvent in multiple steps is able to separate these events and make very monodispersed particles with fairly good accuracy and reproducibility and variability. And for example, they go through and do diffraction to understand the crystallographic structure and growth orientation of particles and kind of rods that are anisotropic, and they have a lot of really nice characterization involved in their result. Another kind of more extended topic that we won't get to talk about in detail, but is, for example, how anisotropic structures are created. And one example that's been done a few years ago is synthesis of these cadmium tellurides, so a semiconductor like we might be able to see in a quantum dot, tetrapods. And so what they mean by a tetrapod is a crystal, a nanoparticle that has these 4 branches. So it kind of looks like, if you play jacks, like throwing jacks on the ground. And by a chemical process that's described in this paper, they find that different crystal facets of this zinc blende crystal structure are passivated by adding a certain chemical to the solution. And in other words, they're able to nucleate and grow these crystals in particular directions by adding a molecule that sticks to the sidewall of the arm and prevents new monomer from adding to the surface of that arm. So you get predominant growth along these directions, and you don't get as much growth. You still get a little growth in these directions. So by controlling the conditions, you can grow these crystals that extend in one direction more favorably than broaden themselves. And it turns out that by changing the concentrations of the precursors in the solution, for example, they have a cadmium precursor and a telluride precursor, and you can change the ratios of the cadmium and telluride precursors, and you can also change the ratio of the cadmium to the ODPA, the acid that's passivating the surface. Under otherwise identical conditions, you can control, for example, the lengthening rate of the arms versus the diameter of the arms. But the basic principle at work here is you're controlling the effectiveness of this surface passivation process versus the lengthening process of the arms. And I don't know a lot of the details, but one thing I've heard about these structures is they were seeking them for use in photovoltaics, where you would take advantage of the optical properties of these semiconductor structures for generating electricity, for generating electron hole pairs in a photovoltaic cell. And it turned out that like the shape of the structures was not so important for that photovoltaic application, but the fact that they were mechanically like little tetrapods meant that if you made a thin layer of them, they would all be standing up in a fairly uniform fashion. So you could create a nice uniform layer of these little semiconductor tripods or tetrapods by taking advantage of their geometry, and possibly also controlling the length and the diameter to give the optical properties that you want.
An anti-cavalry tool from the Middle Ages.
Yeah.
They used to spread them, and you can imagine how the horses hated stepping on them.
So how big were those?
A couple inches.
All right.
Enough to get to the soft spot past the hoof.
How were they deployed?
Spread them out. The infantry threw them out in front of the archers.
All right. Cool.
No charging with your lance in among the
Well, I don't think this paper mentioned that, but maybe
they were used at, I don't, the famous battles between the French and the English in the 100 Years' War, they were widely used.
Okay.
So you can make microscopic cavalry and keep them out.
Yeah, if you had a little person, it might trip over this. There's actually a group at Rice University that has made these things called the nanokids, where they made all these molecules that look like different people. And they have the exact synthesis and so on all worked out. So as we finish up the topic for today, we might ask, well, if we're able to run these processes so we can precisely focus the distribution or separate nucleation growth, I mean, is that enough? Well, in most cases, no, because something we haven't talked about is that you can also get physical aggregation of the particles, whether they merge or whether they just form physically aggregated clusters, even if you are controlling the growth process itself very well. So as we talk later about dispersion of structures, like how we would take these structures and separate them out in solution, isolate them, and also how they're self-assembled, we'll learn a bit about those kinds of techniques. And we saw that in the case of growing the tetrapods, adding this molecule that passivates certain directions is an effective strategy for managing growth in different directions. Similar things can be done, for example, if you have your process going and you've reached a certain size of particles, you can add something to the solution that absorbs to the surface and stops the growth process. for example, then prevents more molecules or more monomers from being added. You can also, for example, change the pH of the solution if that, say, changes the surface charge, and you can physically stabilize the particles. In some cases, you can control the pH for charge stability in conjunction with the growth process, so you keep the particles physically separated to prevent agglomeration, to prevent aggregation, and also to make sure that all the particles get reasonably enough monomer from the solution by diffusion. And we'll talk more about that later. And next time we'll move onward to the idea of growth of nanotubes and nanowires. And more than understanding in detail one specific process, I just want us to get an appreciation for the limiting mechanisms of how these structures form and evolve. And those are the kinds of, that's driven home, I hope, by the kinds of questions that are on the problem set. And those are the kinds of things that you might be asked on the exam. You're not going to be asked, for example, how to control the chirality of carbon nanotubes, or to differentiate specifically between the number of walls, but what might, for example, determine why the length changes with time, or how it changes, or how the diameter of the structures changes with time. And we'll see as we go from nanoparticle growth to nanotube or nanowire growth, we're kind of going from a one-step process, if step means formation of the seed and then formation of the long section, to a two-step process. So we can have this vapor-solid kind of nucleation of these wires from a film case, or we can have cases where we use a catalyst, we use a predefined seed to confine and dictate the anisotropic growth of nanotubes or nanowires. And we'll visit this paper next time. There's a very interesting paper from a few years ago that talks about how semiconductor nanowires, I think these are silicon nanowires or silicon germanium wires, grow at different rates depending on their spacing. And also different sizes grow depending on their spacing. And it turns out that a material is incorporated from the gas phase and dissolves into the catalyst, but material also is incorporated from the sidewall and diffuses along the wire and onto the catalyst and then gets incorporated into the crystal. And the substrate is also important because you have the absorption of material on the surface, and in some cases it diffuses up the wires, and in some cases it just stays on the substrate and grows a film. And this is manifested in, for example, pictures where they are able to pattern individual catalyst particles of particular sizes at particular spacings and plot out how the growth rate depends on the spacing between the wires and the position of the wires. So in this case, you can see we have two big particles on both sides, and because there's more surface area available for precursor to deposit on this wire, it can grow taller, and also it can provide more supply to the neighboring wire by this minority path of diffusion up the surface. So these kinds of exchanges by the principle of relative sizes, sinking or sourcing certain amounts of material, are very important for practically governing the size distributions of structures that we might make. So that's the end for today, and I'll see you all on Monday.